Okay, I'd like to tell you about Lenz's law and finding the direction of the induced current. And so, we've been ignoring that negative sign on Faraday's law because Lenz's law is going to give us that direction of the current. There are other ways to get it, but I'm just going to show you the Lenz's law way. So here's Lenz's law. It goes like this. With Lenz's law, I'm going to give you two versions of Lenz's law, and then I'm going to show you many examples of it. Okay, so for Lenz's law, the direction of the induced current will be to minimize the change in magnetic flux. Okay, so you use Lenz's law to find the direction of the induced current, and the direction is always going to be to minimize the change in magnetic flux. Okay. That just makes sense, and I'll tell you why in a moment. Here's another way of looking at it. This is kind of a personification. You know how we personify electrons wanting to get away from other electrons when really they don't really want to get away from them. We don't think, at least. But in any case, the personification of Lenz's law goes like this. Just as mass resists changes in its velocity, that's sometimes called inertia, the fact that mass resists changes in velocity. It doesn't mind velocity. Mass doesn't mind velocity. What it does mind is changes in its velocity. It resists changes in its velocity. Well, so same with conducting hoops. They resist changes in the magnetic flux inside them. They're like the ultra conservative as far as magnetic flux is concerned. They don't want the magnetic flux to change inside them. And if it does, they're going to create a current in themselves that will minimize the change in flux. Okay? Now that kind of makes sense, because could you imagine if we had a wire that had, let's say here's a circular loop of wire. This isn't a circle. This is the wires right here. This is air inside here. And imagine I had X's. Okay, so we got this magnetic field. And once again, the only magnetic field that matters is the stuff that's enclosed that's actually going through the hoop. Not enclosed, but is going through the hoop. And could you imagine if this all of a sudden started to grow, if the X's started to grow, then what would happen if the current then started to be induced in here, excuse me, in such a way as to get the current to grow more, or the field to grow more. So like you induce a current in here so that that current itself made more X's, which would then induce more current, which would make more X's, which would make more current, which would make more X's. And so there's a conservation of energy thing going here, whereas it would be weird if all you had to do was increase the field a little bit, and then all of a sudden there'd just be this great big field in here, always growing, growing, growing. Like, where's all that energy coming from? Well, in fact, it doesn't work that way. What it does is it minimizes the change in flux. The current, if the X's are growing, the current will go the other way. So I want to tell you how that works. Before we do that, let's just talk about hoops for a second. I am going to be coughing a little bit in here because I have a little bit of a cold here. But if we have a hoop, and if the current in this hoop is going that way, let's just agree on something here. If the current is going this way, then there's two ways to find the field that's enclosed in this hoop that's due to this current. One way is to put my thumb in this direction and curl my fingers. When I curl my fingers, that means that in the hoop, there's a field going out at you guys. Okay? That's one way to get that. So when current goes this way, there's a magnetic field going that way. Now outside, it's going to be down. But you know what? For all this, everything we're doing, it's only the inside that matters. Okay. If it's going the other way, then it's going to be, if the current's going this way, then the field will be down. There's another way to get this, though, and that is that you could use another right-hand rule where you curl your fingers in the direction of the current. So if the current's going this way, you can curl your fingers and the direction of the current will be out at you again. And it's that rule that I'm going to use a lot in these. Okay, I'm gonna go with this second one. So my fingers are going to be the flow of current, and my thumb will be the direction of the field inside the coil. Okay, so let's take a look. So let's say that we have a magnetic field. I'll put the magnetic fields in red. So let's say we have a magnetic field, and let's say there's X's here, and it's going like that. X's. And the X's are increasing. So if the X's are increasing, then this is not going to be happy, to personify this again. And it doesn't care about these outside ones, but the inside ones, it's going to try and stop them from increasing by making its own field that is dots. So the field's going in, so it's going to try and make its own field out. To make its own field out, that means the current is going to go this way. That's the direction of the current. That will give you a field out that will try and slow this field from increasing. Okay, let's do that with dots this time. So we got a bunch of dots. Now if the dots are increasing, then this is going to try and make X's because it doesn't want the field to change. And so it's not just, if I didn't tell you that it was increasing or decreasing, you wouldn't know what's happening in here. In fact, if there's just B and it's not changing at all, it's perfectly happy. But as soon as I tell you that it's increasing, then it's going to try and make X's. To make X's, it's going to go this way. That's Lenz's law. Excuse me. Next one. Let's say have this be X's. And now it's decreasing. So the fact that the X's are decreasing inside, it only cares about inside, then it's going to try and make dots. And so to make dots, it's going to go this way. Oh, I must have got that wrong. If it's to make dots, did I get this one wrong? The B is increasing, so it's going to try, oh, I'm sorry, B is decreasing here. So B is decreasing, and so it's, I'm sorry, I was going to mess you up there. Because B is decreasing, these X's are decreasing, it's going to try and make its own X's this time. So it's going to try and make its own X's, and so to make its own X's, it's going to go the other way. My apologies. Hope you didn't stop that short. See how that makes its own X's now? Why does it want to make X's? Because these X's are disappearing. Come on over here with me. Now let's put some dots in here. That means the field is coming toward us. So now it's going to try, and the B's are decreasing, so it's going to try and make its own field that's coming out. And to make a field that's coming out, it's going to go this way. See how that makes a field coming out? Okay, let's move on over to here. Now we have a current in this wire. And because of that, we have some field here. Now the I is increasing in the wire. So which way will the field be induced in this hoop of wire? This is a hoop of wire. Okay, well if I is increasing, then I'm thinking that there are X's here. Now they're strong here, and they drop off here. They're not as strong out there, but there are X's, and if I is increasing, those X's are getting bigger. And so it's going to try, it doesn't want the X's to get bigger, and so it's going to try and negate that effect by making its own dots. And to make its own dots, it's going to make the current go this way. Yes, dots. Last one for this video. Okay, now if I is decreasing, let's see, we have a field that's going into the page still. So these are X's, but they drop off as you go out. Now the I is decreasing, so that means that these X's are going down, 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 down. And so if they're going down, 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 it's going to try and make its own X's. To make its own X's, it's going to go the other way. You see how Lenz's law works? It's always trying to keep the status quo. So if the x's are increasing, then it will try and make dots. But if the x's are decreasing, it will try and make x's. Okay, thanks. Bye.